Okay, so let me now describe the place and route part of the backend design flow. And we will discuss this mainly from the point of view of a concept rather than the point of view of a tool. There are a few references here. You could just go through the user guide and other references, but mainly this has been just the theory part that I'm going to cover now. So we know that when we start with the HDL, we go through all of these steps up till the synthesis to synthesize a netlist, and then finally the last part is place and route. Although it is just shown as one component here, there's several parts to it, which is what we're going to discuss now. So the inputs to this physical design flow is the synthesized netlist, that is output of synthesis, then the constraints file, which is again the output of the synthesis tool, the left file, the technology left, the macro left, sometimes also a def file is used, design exchange format. It's a format which has layout information. Lib files are also used. These are optional files, IO pad assignment file, and also the script may not be needed if you are using the GUI part of it. But typically it is recommended to use the script, the tickle script. The commands are quite straightforward, so that you don't have to redo the design every time. So the design flow, I'm going to skip this step because this slide, because this is mostly from the tool point of view. So what are the setups that are needed? So I'm going to skip this and go to the next one. So these are the steps involved in doing the what we call the place and route. It's also usually called the PNR, place and route. So the first step is what is called floor planning. I'll describe each of these in the next slides. Then we do power planning, plan where to have the VDD VSS rails, plan where to place the pins, that is the input output pins, then finally place the cells, the library cells, the standard cells. Then we do what is called as a clock tree synthesis here, that is to synthesize the actual clock tree. It's called a tree because it's going to go to different parts of the layout. We do a timing analysis before CTS and we do a timing analysis after CTS. So this timing is not with the actual clock tree, so it is with an approximated clock or an ideal clock. Whereas after you do the real clock tree synthesis, then you do the post CTS timing. Then finally, we go to route, that is connect all the standard cells and then report the actual timing, which is going to now involve and have all the wire delays, the interconnect delays, the correct models, and so on. So that is when the layout is almost complete. So then you do what is called design rule check. This is called DRC, design rule check, and then layout versus schematic checks. So once you clear the DRC and the LVS checks for that particular library, so all of these are obviously library specific, the PDK specific, then you're good to go. And then finally we do extract the RC values. This is the parasitics. And finally you could also extract out a spice netlist from the design for this particular design. You could simulate that with spice and verify the functionality, timing, etc. And the last step is, of course, just what is called a stream out. You stream out the layout, and the layout is typically in form of what is called GDS. So this is the extension. So it comes in a .gds format. So that is why this the whole process starting from the RTL to GDS is also typically called the RTL to GDS flow. So these are the different steps involved. Now let us briefly see what each of these steps look like. So first is floor planning. So floor planning is just like if you were to design or build a house. So how would you plan out the whole area? So you have a given certain area. So you want to figure out how much to give for the core, and design is going, your design or the logic or the standard cells are going to be placed inside the core. That is why it's called a core. The design will be placed here. Then this is what is called the die, the external, the entire component is called the die. but the space between the die and the core is going to consist of VSS and VDD rails. So the standard cells are going to be placed in the core, and the whole thing is called the die. So you have to plan out how much space you need, the width, the length, the area for this. That is why it is called the floor plan. So there are several components to this. If you were to do it in the tool, you'll have to specify what is the offset, what is the spacing, what is the width of each of these rails, and so on. Also the width of the core, is it rectangular, is it square, and so on. So that is what is part of the floor plan. So how do you find out what should be the core dimensions? So you have to find out and specify what should be these core dimensions. So for example, let us just assume that all of these cells are 1 micron by 1 micron in size. So let us say we were going to have just 4 cells in this design. So if you were to place them, you just need 2 microns by 2 microns to place them. That is 4 square microns. So that is all you actually need. But typically this is not how you do the design. So typically what you do is you give um, some amount of extra space. So I'll just come back to the previous slide. So if you were to use this entire area, the core area, and all the cells completely fill into that area, it is called as 100% utilization. You've utilized the area 100%. So let us just go back to the previous slide here. So you have the core, then there is VDD, VSS, and then there is the die. So on a silicon wafer, so typically you do not manufacture just one of these, you manufacture several of these. So it is typically done on a silicon wafer, which is typically of 12 or 16 inches of diameter. So this is how the die is going to be placed. So this is just a expanded view of how this particular die looks like. So now coming back to this, so if you fill in the entire core with all the cells, it's called utilization of 100%, and you should never do that. Or it's also called utilization factor of 1, which basically means the area occupied by the netlist divided by the total core area. So typically, you would like to give some, uh, leave some space. So typically, to add any other cells to optimize, etc. So also you need space for wires and so on. So typically, you would set the utilization factor to 50 to 60%. So all of these are not typically done manually. So if you're doing a digital layout of a digital circuit, typically these are automated. So the tool will have to be told what is the utilization factor, what is the aspect ratio, that is the height to width. So what should be the height to width? Should it be a square? So if it's a square, then the aspect ratio will be 1. If it is a rectangle, the aspect ratio will be something other than 1. So the tool will have to be told all of this, and it will figure out how to place the cells in this core. So for example, if the aspect ratio is 0.5, so this is how it will look like. So it will, the height is 2 and the width is 4, therefore 2 over 4 is 0.5, and that is the aspect ratio. And if you say utilization, you can also set a utilization factor, and it will, if you set it to something other than 1, then it will fill in some part of this whole core area. So this is all part of what is called floor planning. So there could also be pre-placed cells. So for example, you may not be doing the die from the scratch, or you may not be doing the core from the scratch. You might have pre-placed cells, or you might want to reuse certain modules. So you may want to place them already. So you could do all of these in the first step. And these locations, you can also ask the tool not to change these locations if you want them in a specific position. So that is what is called floor planning. So now power planning is this part. So you need to place VSS and VDD. You need to figure out what is the width and spacing allowed by the technology design rule and so on, and also on which layer to be placed, etc. So all of this is part of what is called the power planning step. So you add what are called as power rings. So these are called rings because they're placed in around the die, surrounding sorry, it's placed around the core, surrounding the core, and therefore it is called a power ring. So you will also typically connect these rings here, like shown here. You will route the VDD and the VSS here because if a cell is placed here, you may want to give connection to VDD right here, or VSS at that to the closest point, rather than take it all the way up to that ring. And therefore you will also route this VDD and VSS nets across running across the core. There are also other concepts such as decoupling, capacitors, etc. But uh, we let us not go into details of all of that. So basically, there could be uh, VDD to VSS decoupling capacitors to avoid noise, to reduce the noise on the power lines and so on. So those could also be part of the power planning step. Yeah, so like I said, the idea behind routing and having multiple VDD VSS lines everywhere running across the core is to be able to tap the power from the nearest VDD rail, and also to be able to uh, discharge to the nearest ground rail, and therefore all of these connections are made across the core. So all of this is part of the power planning step. Yeah, so you could also add vertical stripes and horizontal routes to give it connections. So you'll have to make sure that the spacing between these make are meeting the uh, guidelines given for that particular technology. So next you would do pin placement. So for example, let's say you have certain pins. You know how many pins for input and output. So what you would do is typically, if you know where these, if you are specific about where these pins should be placed, uh, then you would mention all of that. So let's say this is the kind of position of the pins that you need, and then what would happen in the placement stage is that the corresponding standard cells, so for example D1 is connected to DFF, so that would be placed closer, uh, this DFF would be placed closer to the D1 pin. So all of those optimizations are possible. So for example, you could do manual placement of pins. You could specify exactly where the pins are needed, or you could leave it to the tool to figure that out.